Roughly 6 centuries ago, the earliest iterations of the sport of golf were played by the Dutch, who utilized incredibly rudimentary equipment. During this historical era, the accepted method for manufacturing a golf ball involved painstakingly stuffing a highly compact volume of wet goose or chicken feathers into a small, hand-stitched leather sack. As the tightly packed feathers dried out over time, they expanded significantly, while the outer leather casing shrank simultaneously. This opposing physical reaction created a surprisingly hard, albeit highly irregular, spherical object. While these early designs were considered revolutionary for their specific time period, they were notoriously expensive, incredibly labor-intensive to produce, and structurally fragile. As time progressed and the sport evolved, substantial technological improvements were systematically introduced to the ball manufacturing process. These subsequent industrial advancements ultimately made the equipment exponentially cheaper to mass produce, vastly more structurally durable, and significantly more aerodynamic during atmospheric flight. Fast forward to the modern era, and the global landscape of golf ball manufacturing has transformed into a massive, highly regulated industrial powerhouse. Today, the international golf ball market represents a staggering financial sector, consistently bringing in approximately $550 million in annual global sales. To satisfy this massive consumer and professional demand, major industrial facilities are responsible for manufacturing and shipping well over 850 million individual golf balls every single year. So, how exactly are these modern marvels of sports engineering systematically fabricated from raw chemical compounds into the highly precise projectiles utilized by professional athletes today? The foundational core of the modern golf ball is typically constructed from a highly specialized synthetic polymer material known scientifically as polybutadiene. Manufacturers do not select this specific chemical compound arbitrarily. Polybutadiene is heavily favored within the sporting goods industry because it offers a highly unique combination of extreme structural resilience and exceptional long-term durability. More importantly, this specific material possesses an incredibly high coefficient of restitution. In the realm of physics and sports engineering, a high coefficient of restitution means that the material has the extraordinary ability to violently deform upon high-velocity impact with a club head, absorb that massive kinetic energy, and then almost instantaneously regain its original spherical shape. This rapid structural recovery translates into explosive exit velocity and high ball speed. Before this polybutadiene rubber can be molded into a functional core, it must be chemically synthesized from scratch. The raw material itself is created through a complex chemical reaction known as polymerization. While there are multiple distinct types of polymerizations utilized across various industrial sectors, the specific process utilized to synthesize the resilient material we are after for golf balls is referred to as solution polymerization. During this chemical process, the base monomers are completely dissolved within a hydrocarbon solvent. A specialized catalyst is then introduced, linking the individual molecules together into long, resilient polymer chains. Once the raw polybutadiene rubber has been successfully synthesized, it must be carefully prepped and compounded. The raw rubber is transported into heavy-duty industrial mixing machinery, where it is aggressively combined with various necessary chemical additives and proprietary fillers. These specific additives are mixed and prepared according to the desired chemical formulation. During this intense mixing phase, the entire compound is heated to specific temperatures and physically softened for significantly easier downstream processing. The continuous mechanical churning and thermal energy transform the initially tough raw rubber into a highly viscous substance that closely resembles the thick appearance of standard cake batter. Following the thorough mixing stage, the newly prepared polybutadiene material is continuously fed directly into a massive industrial mechanism consisting of a series of heavy calendering rollers. These massive, highly pressurized cylindrical rollers are typically forged from hardened industrial steel or other durable metallic alloys. As the heated rubber compound is mechanically forced through the microscopic gaps between these rapidly spinning cylinders, it is flattened and compressed. The raw material smoothly exits the final set of rollers in the form of continuous, perfectly uniform, and condensed flat sheets of uncured rubber. Once these continuous flat sheets of uncured rubber are successfully formed and adequately cooled to maintain their structural integrity, the production line transitions to the physical sizing phase. The immediate next step in the manufacturing process is to precisely cut or punch out small, proportioned cylindrical slugs from the massive sheet material. Specialized cutting dies or automated punching machines are utilized to systematically create these identical rubber slugs by the thousands. Every single slug is calibrated to contain the exact volume and mass of rubber required to form one single core. The freshly punched cylindrical slugs then travel continuously along an automated conveyor belt system over to a massive hydraulic compression molding machine. At this station, a human worker or an automated robotic arm carefully places the individual rubber slugs directly into the hemispherical cavities of heavy-duty steel molds. Once the loading sequence is complete, the heavy safety doors seal shut, and the molding cycle initiates. The bottom section of the steel mold presses upward with immense hydraulic force against the stationary top section, sandwiching the rubber slugs and applying over a full ton of localized pressure. Simultaneously, the newly rounded rubber material is actively baking at an extreme temperature of exactly 160 degrees Celsius. This combination of heat and pressure is maintained for a strict duration of exactly 13 minutes to harden the rubber. Immediately after the heated curing cycle concludes, the solid cores must be rapidly cooled. Cold water is circulated through internal channels within the steel molds to drop the temperature and stabilize the material. Once fully cooled, the massive press opens. A factory worker then places a specialized piece of slotted plexiglass directly over the open mold cavities. This specific sheet physically holds down the thin, leftover rubber trimmings, ensuring that only the perfectly spherical ball shapes get cleanly picked off and extracted from the mold by an overhead vacuum system. While the internal cores are being formulated, the outer casing of the golf ball is manufactured entirely separately in a different sector of the facility. The specific chemical composition of the casing material can vary significantly, but it is most commonly constructed from a highly durable blend of proprietary ionomer resins, or a softer synthetic urethane. This chosen casing material is subjected to thermal heating until it reaches a pliable state. It is then mechanically formed into thousands of uniform, thin spherical hemispheres. These individual shells are colloquially referred to on the factory floor as the top and bottom halves of the cover. With both the hardened internal cores and the external casing hemispheres fully prepared, the manufacturing process moves to the critical assembly stage. A single solid polybutadiene core is mechanically placed directly inside one of the casing hemispheres. To ensure maximum structural integrity and prevent any internal slippage, the interior concave surface of the casing is often pre-treated with a specialized chemical adhesive or a bonding primer. Following the primer application, the corresponding opposite hemisphere is aligned and placed directly on top, completely encapsulating the core. The two independent halves are then forcefully pressed together, utilizing extreme high pressure to ensure an absolutely secure bond between the core and the outer shell. These newly bonded units are immediately transferred into another heavy-duty compression mold for their final structural shaping. This secondary mold features the iconic dimple pattern and the final desired spherical shape intricately engraved directly onto its inner metallic surface. These microscopic dimples are crucial for aerodynamic performance. Dimples actively help to aggressively reduce atmospheric drag by creating a turbulent boundary layer of air that adheres closely to the ball's surface. Furthermore, this dimpled texture works in tandem with the ball's backspin to provide essential lift during its flight trajectory. Immense heat and hydraulic pressure are applied to the mold. This intense physical force simultaneously compresses the internal core and the external casing together, securely fusing the two layers while permanently embossing the complex dimple pattern into the exterior shell, officially giving the ball its final functional shape. Immediately after this secondary compression molding cycle is complete, the freshly shaped golf balls are forcefully removed from the heated mold and are instantly on the move. They roll down a steep incline into a large collection bin. This collection bin systematically funnels the stream of newly molded balls directly into an automated vertical elevator system.
As the balls exit the molding process, they exhibit a thin equatorial seam of excess plastic where the two halves of the mold met. This excess material, known as the flash, must be cleanly trimmed away. This critical finishing step is done completely automatically through a specialized automatic miller, which carefully shaves and removes the excess plastic. Immediately following the flash removal, the entire exterior surface of the ball is aggressively polished, using abrasive tumbling compounds to ensure a perfectly smooth finish. With their physical construction fully complete, the pristine golf balls must then undergo incredibly rigorous quality control checks. This comprehensive auditing process includes precisely measuring the exact total weight, the geometric size, and the physical compression ratings of the balls, alongside visually inspecting them for minor cosmetic imperfections. One highly effective mechanical way the factories execute this precise physical sizing is to use automated robotic arms to rapidly shuttle the newly finished balls directly through a highly calibrated chute entry. If the ball is not perfectly smooth and uniform, it simply won't fit. Only the elite tier of golf balls that flawlessly meet all specified standards are permitted to move forward toward the next logistical step. A mechanized wheel rapidly rolls the verified balls towards an automated stamping machine. Here, fast-acting robotic arms carry specialized ink-covered silicon pads directly over to an etched steel plate. These highly flexible silicon pads pick up the precisely metered ink from the engraved plate and gently press it onto the curved, dimpled surface of the ball. This intricate pad printing process is how the completely blank spheres are officially branded with a specific corporate company name, a designated player identification number, and the technological ball type. Immediately after the logos are stamped onto the surface, the ball passes under an intense blast of high-frequency ultraviolet light, which rapidly hardens the specialized ink. Following the UV curing, an advanced automated machine aggressively sprays the entire exterior of the ball with a high-gloss protective clear coat of polyurethane, while the balls rapidly rotate atop mechanical spindles. This durable polyurethane barrier permanently protects the newly applied ink logos from aggressive wear and tear. Finally, synchronized robotic arms gently carry the freshly coated balls directly over to a massive drying rack. The entire rack is transferred into a specialized convection oven where the balls are consistently heated at exactly 66 degrees Celsius for exactly 5 minutes. The balls are finally considered fully done, packaged, and shipped. A single completed golf ball can feature anywhere from 300 to 500 dimples,